Okay,
Yes.
great. So thank you again for joining us on the final event of our summer series, the RF microwave webinar series. And I'm David Brown. I'm the president of Berkeley Nucleonics, and I'm joined today by Junior Che, the RF product line manager, and also John Lauder, who's our senior RF engineer, who's going to run some live demos on his computer on the instrumentation. And without any further delay, everyone's time is valuable, and I appreciate you joining us on a Friday. Let me turn this over to Junior.
Yes, thank you, David. And thank you, everyone, for joining today. Yes, welcome to our Berkeley Nucleonics webinar series. This is our final iteration for this series, but we will definitely have more in the future. Again, my name is Junior Che. I'm the RF product manager here at BNC. I have Mr. John Lauder here next to me, or virtually next to me, as our senior engineer. He will be giving us a great demo on low-level pulse measurements with our phase noise tester. So before I jump into the presentation, I just have a quick overview about the webcast in itself. So first, this webcast will be recorded and a link will be emailed to all of our attendees. All of the participants will be muted until the Q&A session at the end of the presentation, but you're more than welcome to type in any question in the chat box. It should be on your lower left-hand corner of your screen, or possibly even on the right, depending on your layout, but there is a chat box there for you, so please feel free to enter in any questions. You may want to expand your presentation window. There is like a little arrow, 4 arrows that are spreading outwards on the corner of the screen there, next to the ID number. That will bring you into a full screen mode, maybe better in terms of visual. And then you can always minimize back by hitting the escape button on your keyboard. Now, we'll say that the chat box is not private, so all of the attendees will be able to see your question, your comment, or maybe even a joke. So please be mindful of that. But the presentation is definitely not classified, so you're more than welcome to send it out to any of your colleagues, friends, family members, whoever you may feel would benefit from this presentation. So wanted to really quickly touch on our company itself. You know, Berkeley Nucleonics Corporation, we've been in business since 1963 by offering one of the world's first NIM, or nuclear instrumentation modules, which is basically a pulse generator for the nuclear industry. Now, today, we have 3 divisions of our company. RF microwave, obviously, test and measurement with our pulse generators, including our Model 575 or 577. Possibly you may have heard of this unit or have experience with it, as it is one of the staples in the timing industry today. And finally, we have our nuclear division. You know, we have full solutions from personal radiation detectors, isotope identifiers, and all the way up to custom scintillation detectors. So again, please do let us know if you have any questions regarding any of our capabilities and solutions. So another tidbit here. I wanted to highlight our worldwide network of sales and service representatives. So if you look at the map there, you'll see we pretty much have every major continent covered. So, and I do notice some overseas attendees here. And again, thank you very much for joining us today. I know it may be pretty late in your time zone, but you can be rest assured that we would most likely have a local representative in your area that can provide support for you on our behalf. And of course, here in the U.S., you can see the image to the right. We got the U.S. covered as well, domestically, from the East Coast to the West Coast, South and North. So again, if you have questions about our solutions, we're more than happy to direct you to your local representative. So diving right in, the agenda for today's presentation. Our main focus here will be radar. What is radar? Just the basics of radar, the components of a basic radar system, pulse versus CW radar systems, and the types of pulse radar. And that will be our second key term, is pulse, since that is the demonstration that we'll be providing today. We will be going over the different types of pulse radar systems. And then, of course, pulse phase noise measurements, as we will be doing a demo with our own PNT. So we'll be going over the importance of that type of measurement, and of course dive right into the phase noise tester in itself. And then John Lauder will provide a great demonstration for you on some low-level pulse measurements. And then finally, we will have our Q&A session. Again, you're more than welcome to type in your questions in the chat box, but you can even join us for a discussion. We will unlock your microphone, unlock your camera if you have one, and you can join us with the screens you see there. And then your face will pop up right there, and you can ask us questions, and we'll have a discussion. So let us dive right in. The first subject here is radar, right? What is radar? The basics of radar. Well, many of you may already know the acronym. The acronym stands for Radio Detection and Ranging System. It is basically an electromagnetic system used to detect the location and distance of an object by monitoring the echo or reflected signal. So if you look at the simple image above, the basic radar system will have a transmitter and a receiver and an antenna. So the transmission system will send a signal to your target object. And as you can see, the black arrow is your transmission line or your transmission signal. It will be reflected as an echo signal, returning back to the same antenna. And then the antenna will send it to the receiver for analyzation. And I will say that this returning line is the crucial part of the puzzle. This will give you all of the information on the location and the distance and other types of parameters that you are looking for. Now, there are many different types of applications for radar. You may already know, whether it's military, tactical surveillance, air surveillance, ground surveillance, commercial side, air traffic control, weather reports, and so forth. And the list goes on. But again, we will be tackling just the basics of radar and especially pulse radar systems. So let's talk about the two main types of radar systems. We talked about pulse. That is going to be our focus. So the basic pulse radar system is sending pulses toward your target object. You're waiting for that echo signal to return. And once you have received that signal, you are sending another pulse back. Now, the basis or the main goal of the basic pulse radar system is to determine the range or distance of that target object. And in order to do this, that return signal, that echo signal, will have your pulses, which will be a little bit different from what you sent from your transmission signal. So, and that is what you will be analyzing, basically the time intervals in between these pulses. That will determine the actual distance or the range to your target object. Now, we'll say that for the basic pulse radar system, the system is non-coherent because the phase is random from pulse to pulse. That is quite important, especially with phase noise testing, as we will be getting into later on in the presentation. Now we'll also talk about phase coherent pulse radar systems as well. But the main application for a pulse radar is long-range air surveillance. Using pulses will give you a little bit of a better advantage on that range. You can cover a lot more ground, and that is due to your ability to manipulate the pulse. And you can have a wider pulse or wider interval, higher rep rate or lower rep rate, and these will determine the type of range that you can cover. Now, the other type, or the second type of radar systems, is the continuous wave or CW radar system. And instead of sending pulses, you are sending a CW signal at a constant frequency. Now, the received signal will include a Doppler shift, which is used to determine the target's speed or velocity. I will definitely get into what the Doppler shift actually is, because that is where you're going to determine the velocity. But the basis of a CW radar system is to detect speed. As you know, a great example would be law enforcement. A police officer with his radar gun monitoring traffic to look for speeders. That is called a CW Doppler radar. And again, that is the most used type of application for this radar system. Now, I mentioned the Doppler shift. So let me explain how you figure out the velocity from the Doppler effect. So back to that same example of the police officer shooting out his CW signal at a single frequency. As you can see on the image here, the radar will send out a transmission signal at that frequency, and then it will bounce off the moving object, and the return signal will give you the information. Now, as you can see here, the top transmission line of the approaching vehicle, that transmission line is a little bit different, or that return line is a little bit different from the transmission line. As you can see, the wavelengths have shortened quite a bit, the intervals as well, and also the number of wavelengths. Actually, the number of wavelengths will indicate which direction that object is traveling. So in this case, it has an increased number of wavelengths compared to your transmission line. That will indicate to you that that object is approaching you, or the direction of yourself. Vice versa, the wavelengths for a receding or a object moving away from you will have a much wider wavelength and a less number of wavelengths. And again, that is that indicator that the object is moving away. In order to calculate the velocity or the speed, you would actually have to look at the frequency shift. So as you can tell, again, the return line, that frequency will be different from the transmission. That frequency shift is actually what the Doppler effect is, or some may call it the Doppler shift. By knowing this shift, by knowing exactly what this frequency is for the shift, you can calculate the velocity instantaneously. Due to the fact that this is a continuous wave, your results will always be continuous, and you can instantaneously measure that change of rate of the range of that target object. So also, I must mention for stationary objects. This is for moving objects, right? And that returning signal will always have a frequency shift. But for stationary objects, that return signal will almost be identical to the transmission signal. They will have zero frequency shift, which is also called zero Doppler shift. I will explain why this is quite important as well for some other types of radar systems in the coming slide. So let us talk about the key components of a pulsed radar system. As you may know, there may be many more components depending on the need, the application, the requirements. But in this case, I'm just going to go over to the basic components. So number one, obviously the transmission side, right? You will need some type of signal source combined with a power amplifier, most likely a pulse modulator as well. That will transmit your signal. You would also obviously require an antenna. This could be many different types of antennas, including phased arrays, which will account for the multiple different angles and directions that you may want to cover. A duplexer, this is very important as well. This allows you to use a single antenna, and that will decide whether to transmit or receive a signal from that same antenna. Then also the receiving side. This is very important as well. This will determine if the receiving signal is worthy enough to be detected and analyzed. Once so, it will then be sent over to the indicator or display. It's very, very basic. We would need an understandable graphical picture for the end user to know exactly what the target object is doing. And the basic the graphic here will just show you basically how the signals move, right, from your transmission side to the receiving side and to the display. So let's get into the two most common types of pulse radar. The first, most common, is the pulse Doppler radar. Now, as I mentioned before, the basic pulse radar system is really used to determine the distance or range of that target object. But what if you would also like to know the velocity of that target object? This is where the Doppler effect is now incorporated into that same pulse radar system. Same concept. You're sending a pulse. You're receiving this a pulse signal back as an echo signal. You're going to analyze the pulse intervals to determine the distance, but also you're going to receive a frequency shift from the Doppler effect component that you have added to this pulse radar system. So now, not only can you measure the distance, but you will also be able to measure the direction and the velocity or speed of that target object. So if you look at the basic diagram below, this is just a basic block chart of a pulse Doppler radar system. And if we look at the transmission line here, the transmission portion of the system, it starts with your CW oscillator or signal source. Since it's a pulse system, you will have some type of pulse modulator to manipulate that sine wave into a pulse. You will add some power and also make sure you have the correct level of power for each pulse. Then it will be sent to the duplexer. Duplexer will know that this is a transmission signal and let the antenna send it out to the object. Now, once it bounces back as an echo signal, it'll hit the antenna. The duplexer will now recognize that it is receiving, allow the antenna to receive, and then send it to the receiving system. That is a bottom portion of the block chart. The main portion of that receiving system will be the detector. The detector will also have an LO or a local oscillator within that as a component as well, and that will determine the minimum signal requirements. So if that returning signal does not meet the threshold, it will reject and not even detect. So once it has met the threshold, it will then be analyzed, sent over to the Doppler filter. This is the main component for the Doppler radar. That is where excess noise will be removed. And then your frequency shift, or the Doppler frequency shift, will be produced. And that is where you can instantaneously determine the velocity or target object, velocity or speed of the target object. Now, I must also mention that this system will be phase coherent. As I mentioned earlier, the basic pulse radar system has a random phase from the pulses, but due to the fact that you have added the Doppler effect, that will allow the system to stay continuous within phase. And that is important as well for phase noise measurements. Now, there are many different types of applications for pulse Doppler radar. The main, again, is for air surveillance. You are on the ground. Possibly you're looking for certain types of aircraft in your airspace. You would target an area, find the aircraft, find out how the distance of that aircraft, and also the direction and velocity. The second most common type of application is the weather report. We put that the image there for the Doppler radar. Many of you have seen this, watching your local weather report. This is a system that they're basically using. So instead of targeting a quote-unquote aircraft, they will be targeting a storm cloud. Whether it's miles off the coast or wherever you are located, they're able to go pretty long distances. Again, pulse radar The benefit of that is the distance covered. So you're able to go out pretty far and able to locate a storm cloud, determine the distance of that storm, the direction it is traveling, and also the speed. And this is the reason why they can give you so accurate results on your local weather report. You know, on Friday at 5 p.m., that is when the storm is going to hit. And I used to always wonder how they did this. That is due to the accuracy of the returning signal of pulses, you know, able to analyze the intervals. And it's quite accurate in terms of that distance and velocity. So moving on to the next type of pulse radar, very common as well. This is the moving target indicator radar, or MTI radar. So as I mentioned before, you know, for the pulse Doppler, you are most likely surveilling the air from the ground. But let's flip that scenario. You know, let's say you are in an aircraft now trying to lock onto a moving object on the ground. You're looking for that one return signal from that moving object so you can find out how fast, you know, how far that object is traveling. But in reality, you will most likely receive multiple echo signals. And that is due to quote unquote environmental clutter. And that is the basis for MTI radar to be able to remove that environmental clutter, these echo signals from these clutter objects, and be able to lock onto your moving target. Now, as I mentioned before with the Doppler effect, any moving object, your return signal will always have a frequency shift or a Doppler shift. But for stationary objects, that return line will be the same, right? There will be zero shift or zero Doppler shift. So with this system, they have incorporated an extra component called the MTI filter, also called a double canceller. That is the schematic you see right below on the left here. That schematic of the MTI will allow the system, this filter, to instantaneously remove all of these zero Doppler shift signals, remove all the environmental clutter, let us stay locked on to the moving target. The image to the right is basically a real-time visual, I guess. You know, it's an image, a snapshot of an MTI radar in action from an aircraft. And as you can see, it can lock onto multiple moving targets. These little square boxes, those are basically vehicles. All of the other environmental clutter, like the buildings, it could be any type of terrain, hills, mountains, all of those signals will be canceled out. This is quite important, especially for military applications, but also in commercial as well, especially for air surveillance, for maybe traffic and or at air traffic control and so forth. So let us take a quick little break here before I go on. Normally, we would do these types of presentations by inviting you to a local restaurant. We'll provide lunch, obviously, and have some great discussions about, you know, certain applications, our solutions on what we can provide for you, and then, of course, provide support for your requirements at that moment. But due to the conditions of today's, you know, world, obviously that's a lot harder to do. So knowing that, we still do want to provide some lunch and a t-shirt. So in order to do this, we need your help as well. So I'm going to pop up a button on your screen.
And I'll demo the t-shirt here while you're doing that.
Thank you, David.
Yeah.
Boom. You should have heard a little bell. If you just click on that button, it'll take you to our contact form. All you would need to do is type in where you would like us to send you your gift card, your t-shirt. Please let us know your t-shirt size, and we'll make sure to get that out to you ASAP. Now, I do not know which restaurant it will be. It will be definitely local to you, but I can promise you it will not be Wendy's.
Ah, the secret. And so we've got a lot of these shirts that were made up for the IMS. So we'd love to provide for you the t-shirts as well. They're pretty sweet. People love them, but just make sure you put your size. Small, medium, large, XL or 2XL. And Brian, we'll pick a steakhouse for you. Absolutely. We want to make it. We appreciate your time, and we want to do things the right way at PNC. So we got you guys. Thank you for the chats. It makes it a lot of fun. I'll let Junior continue.
Thank you.
The demo. We'll get shortly to the live demo screen share shortly here.
Yes. So moving on, we talked about the basics of pulse radar systems and how they work. Let's talk about phase noise, right? Why is phase noise important for pulses, right, and pulse radar systems? Well, I don't know if you have joined us for our earlier webinars when we talked about the basics of phase noise, but let me just quickly give you an overview of phase noise in itself. So phase noise is the frequency stability of a signal, more specifically within an oscillator. Now, if you can imagine, any type of communication signal, data communication signal, data link, even your cell phone, right? And if you have a noisy background, or the person on the other side, his or her voice is getting choppy, hard to understand, well, that's basically phase noise. And that's why it is quite critical for any microwave RF designer of a system to understand where their phase noise is coming from, to build a strategy to mitigate this noise. Now, if you look at the images to the right, the first image here is what's called, quote unquote, an ideal signal. And as you can see, the sine wave is very clean, nominal amplitude, nominal frequency. The spectral density line below is straight and narrow. Again, this is, quote unquote, an ideal signal, not what you would see in the real world. So if you look to the right, this is indicative of what you would actually see. Random amplitude changes, random phase changes. Your spectral density line below, obviously not clean and straight anymore. You have some noise on both sides of the band. So again, it is critical to understand where your phase noise is coming from, so you can build a strategy to mitigate this noise. Therefore, you can expect the best results from your system. Now, with radar systems, the same concept applies, right? If you look back at this block diagram of that pulse Doppler radar, let's look at the transmission line. So I'm going to put up a pointer here. So and excuse me for the. Hopefully, you guys can see this. So the top three components, this is where your transmission will be created, from your signal source, the CW oscillator. Well, that signal will be sent to your amplifier. Your pulse modulator will manipulate that CW signal so you can create the pulse of your requirements. The power amplifier will make sure that there is the acceptable level of power for each pulse that will be sent to the duplexer. So the transmission line here is quite important, because if you have a noisy signal source, or if you have noise from your amplifier or noise from your pulse modulator, that is going to affect this signal that is going out from your antenna. So just like a regular microwave RF system, where they want to make sure that the communication is clean, in this case, you want to make sure that your results are clean. As we're trying to find out how fast a target object is moving, or how far of a distance is that object. The results are critical, right? We do not want to have too much variance in these type of results. So again, the same concept applies. Noise is critical to the overall performance of your radar system. Also, I must mention on the receiving side, as I mentioned before, there is a local oscillator on the receiving side, and that local oscillator will have a minimum signal that will allow the return signal to even be detected and analyzed. So if you have too much noise on your outgoing transmission line, that return line may have even more noise. So in order for it to be detected and meet the threshold from your LO oscillator in the receiving side, you must make sure that you have the lowest noise possible from your transmission line. I will get rid of the marker. Okay. So let me move on to the next slide here. Another really important reason why you must know what your phase noise is for your pulses. So as you can see from the images, the one on the left is a CW carrier, right? As carrier, a spectrum line or spectral density line, and that's the representation there. So once it is modulated by amplitude to create a pulse waveform, the sine wave represented by each spectral line in the pulse waveform spectrum produces two sidebands, an upper sideband and a lower sideband. So I'm going to bring out my pointer one more time. There. So again, this is your CW wave, CW signal, your carrier. This is the modulated signal. Now you have created a type of pulse. And here are the upper and lower noise bands, and also the spectral lines, additional spectral lines, right? The modulation process alias the noise of the CW carrier onto each of the sideband lines of the pulse carrier spectrum. So the noise, again, mistakenly aliased onto each spectral line. So now you have additional noise compared to your original CW carrier. That is quite important as well. Another reason why you need to understand the phase noise levels of your pulses, because again, that is going to determine the type of results you will receive from your transmission or receiving line, and it will determine the accuracy of your results, whether it's that distance or speed. So with that said, let me get into our phase noise tester, right? And I'm not going to go over every single feature and function. As you can see, there are a ton, and we can cover many, many, many different types of applications. But today we're focusing on radar. And I've highlighted here the types of phase noise measurements that our PNT can measure for you strictly for radar type of applications. So CW, so if you have a CW Doppler radar signal, you can measure that with our phase noise tester, since CW waves will be phase continuous, phase coherent. Your pulsed radar as well, as long as it's a pulsed Doppler radar system, or you have amplitude, you're using amplitude modulation to manipulate your pulse or create your pulse from the CW signal, it is phase coherent, and our PNT will be able to detect that signal and analyze burst measurements as well. So again, our PNT can be used to analyze many, many different types of radar signals. And again, many different types of features and functions I won't get into, but if you do have questions and other types of applications, we're more than happy to support you. So this is a time for John Lauder's demo. So first we're going to show a video demo. And then once the demo is finished, John will do a real-time live screen capture of a low-level RF pulse measurement. So with that said, let me pass it over to John. Thank you again for doing this.
And just a quick reminder, once John starts the video, you may have to tap to unmute on your screen to get the audio for the video. And if you use the little 4 arrows next to the ID number of the session, that will expand your video so you get the full experience. Go for it, John.
Well, thank you, Junior, and thank you, David. First, again, we'll do some video that we pretty much captured earlier. Let me do play now. Hello and good morning. Welcome to today's pulse phase noise measurement tutorial using BNC 7000 series signal source analyzer. What I have here is a 15 gigahertz RF signal. It is a CW or continuous wave with about 13 dBm of power. As you can see that my signal is automatically detected by the phase noise analyzer and as the power as well. I also made a phase noise measurement of the CW signal so we have a reference. To make a pulse measurement, simply activate the pulse mode. Here you have the PRF and the duty cycle of which the device can automatically detect, or you can enter it for a faster processing. If you switch to time domain mode, you can see that my signal is still a CW. Going back to my signal generator, I'll go to my modulation tab. Here I have a pulse rate of about 50 microsecond and a pulse width of 0.5 microsecond or 500 nanoseconds. I can let the device or the PNT automatically detects this information, or I can just enter it for a faster processing. For a 50 microsecond, that's about 20 kilohertz, and that's about 1% duty cycle. And going back to my signal gen, I will now activate the pulse modulation mode, and then the PNT automatically detects that the input is now a pulse, of which is about 1% duty cycle. To make measurement, simply click measure, and the unit or the PNT will start locking to my 1% duty cycle. It detected the right PRF and duty cycle. So here it's trying to lock. Also on pulse measurement, the smaller the duty cycle or the pulse width, the longer it will take to lock. So it will take us about a minute or maybe a bit more for this to lock. While we're doing that, in fact it did lock right away. It takes about 30 seconds to lock it. So, and it will take about estimated 35 seconds, probably more than that, to complete the 10 correlations. And if you switch to measurement tab, you'll see that the partially correlated pulse measurement. Click on select. It also detects the pulse width, duty cycle, and the pulse rate. Also in pulse mode, the maximum offset you can see is the pulse repetition rate. In our case, it is 20 kilohertz. Okay, it's complete the measurement in about 1.6 minutes total. That's including the locking. And we have the plot or the trace on the absolute phase noise tab. Also, if you're trying to measure the phase plot of a pulse using an amplifier, it also supported an additive phase noise and as well as the amplitude noise tab. That's how you make pulse measurement using BNC 7000 series. Thank you. Bye-bye. Okay, we're back live now.
Yep.
Okay, so now we'll do a quick, again, a demo, a live demo of measuring pulse measurement. Again, what I have here is a Berkeley Nucleonics Model 855, a 4-channel, multi-channel, phase-coherent signal generator, and the output is directly connected to the DUT input of the phase noise tester. In real world, again, as just Junior mentioned earlier, for a pulse measurement in general, you measure on after the power amplifier, which basically the output will be pulse RF, and after the duplexer, or in most cases, it is after the receiver. So going back to my signal gen. Okay. This time I have a frequency of 10 gigahertz, which is on the X band, mostly commonly used frequencies in radar systems. I also have my pulse generator set to 50 microsecond rate and about 5% microsecond pulse width. That's about 1%, 10% duty cycle. I also made a phase noise of 10 gigahertz CW, so we have some reference. To make pulse measurement again is to simply enable pulse. And I'll go to my signal generator and enable pulse as well. So you can, again, either enter the values here or you can let the device detect the pulse. That's about 20 hertz. I did detect it right away. And if you need to set your offsets and correlations, just enter it prior to measuring it. For measurement, just simply click measure. And again, the device will start to lock to our pulse signal. So it's locked right away. It took about 12 seconds to lock for a bigger pulse width. As I mentioned in the video, that the shorter the pulse width and duty cycle, the longer it will take to lock. So it's now making some correlation of the pulse. Okay, correlation plot is completed. So again, you can easily set the markers to analyze the phase plots. I'll give you back to Junior for continuation of the webinar.
any questions about the measurement that John just made from our attendees? We'll have a live chat in a second here, but if you want to drop them in the chat box, we can try to adjust the measurements for different applications. But I'm gonna, Junior, unmute you. There you go, Junior. Okay.
Okay. So thank you again. Yes, please enter in all your questions. If you would like to see maybe some different parameters, pulse parameters, we'll try to do another demo for you. But moving on, we're almost at the end here. And I must mention our BNC Academy. You may have heard about this from us before. We're very excited. It's still quite new. And by announcing this, we want to get your feedback. So there is a free code for you to access any of our courses. Again, completely free. There's no charge. Again, all we ask is your feedback. If you'd like to see improvements or any suggestions. Again, continue to improve this, and eventually we would like to have a full-on academy with many, many more courses. So I'm going to pull up another button here. It'll ring, and all you have to do is click on that button. It'll take you to the academy page. Your code here is Berkeley in all caps. Just type that in where you would actually type in your credit card number to pay for the course. Just type in that code. It'll give you free access, and it'll look something like this here in terms of the page of the course. Some examples you see. We have an RF boot camp, the basics of RF in general, the basics of precision timing, with digital delay generators and large area timing solutions, even nuclear and radiation. Right, we have courses all across, since we have 3 divisions of our company. So again, they're all there for you. You can take any course you would like, even if you are not a nuclear expert. Maybe you just want to, learn a little bit about it. Well, that's there for you. And if you have any feedback, suggestions, we'd love to hear it. So that is about it for our presentation. I guess it is time for some questions. Again, you can type in your questions in the box, or if you'd like to join us, and ask us a question directly, we'll unlock your microphone. So all you need to do is click on the microphone icon next to your name, and it'll just ask us, is it okay? And we will grant you the opportunity to come in and jump in with us and have a discussion.
I'll give that a shot here. Okay. Now anyone who wants to click on their microphone is live, and any Q&A. First question from Javier. How would you compare, this is a great question for you, Junior, the RPNT to the 5052?
5052, yes. It compares very well, very, very well. And we actually have many, many customers, coming from a 5052, and we recognize this even with our design of our 7300 series phase noise tester. So we also understand the 5052 is no longer, it's end of life. You can still obviously, find solutions on the refurbished market, and they may even provide a refurbished unit for you. But in terms of performance, it's the same cross correlation. We have very, very low noise floor, at minus 190. I would suggest that you do some comparisons there in terms of, that spec and all the other functions and features too. We compare very well, both additive and absolute measurements. And let me also mention the additive measurements that we provide is at no additional cost. That's a main difference between the E5052 as well. But if you have additional questions on how we compare, please do let us know, and we're happy to possibly send you a demonstration unit for your evaluation. You can do a comparison yourself, even side by side, if you have a 5052. I encourage that.
My understanding also is in the ATE modes, our measurement speeds are much faster.
Definitely, yes. I'm sorry I didn't mention that, but Not even in ATE mode, just in yes in ATE mode, but in general, our measurement speeds, absolute measurements, additive measurements, you'll notice that the actual speed in itself is quite fast. I would say into the microseconds, depending on the parameters that you have set.
Okay. Another question: what is the purpose of the service agreements?
Well, service agreements, that is for your protection, right? We obviously offer a great warranty for all of our equipment. In this case, our PNT or signal generators would come with a 1-year warranty, fully backed with complete support. Any type of repairs needed, that is all covered. But what if you need yearly calibration? Right? Or you may not want to worry about, warranty services after a year. So we have some service agreements that extend that service out. Right now we have a 3-year service agreement we like to make our customers or prospects aware of when they are asking for pricing for any of our products. And additionally, that this 3-year service agreement will not only give you that warranty, but we will cover any types of repairs, the shipping costs back and forth, and your annual calibration. So for 3 years, your calibration is covered. You send it to us. We'll do all the work for you, give you all the data that you require coming back. And again, we want to make it as seamless as possible, the easiest ownership as possible. We pride ourselves on that service and support that we offer.
Okay.
Javier Hernandez, I see, is typing something. I wonder if that is the famous Javier Hernandez, Chicharito. That'd be very, very cool if it was. Oh, I guess maybe it is the real Chicharito because he stopped typing.
Yeah. Okay.
We'll wait a second for the question. I see he's typing, but I think that might be wrapping it up for the questions, and if there's an additional questions after the presentation that you may come up with, our information is there for you. You can always reach out. We will provide that support that you require.
Yeah, we do have some comparison tables on the E5052. And so we'll send that along with the conference wrap up. Another question about a front panel screen for the PNT.
Yeah, that's something that we are actually developing as we speak. It may, I don't have a timeline on when that will be available, but something that R&D and myself, we've all been sort of discussing, as that has been a request as well. Right now, our PNT is strictly, PC control only, and one of the reasons for that is it really helps reduce the cost of our PNT compared to a full touchscreen with all the buttons of these competitors. And we also recognize those components, whether it's the screen or the buttons, they tend to go bad over time, right? So we thought that was a better idea to get rid of, that type of reliability issues that may pop up in the future, and also reduce the cost, which is many of our customers do like. But we have gotten requests, the I guess flexibility of having a front panel. We do understand that, you can make your, you set your parameters a lot quicker that way if you're in front of the unit itself. So that is something that we will announce, I wouldn't say shortly, but keep an eye out. We are definitely developing a solution there, a different type of enclosure.
I put just a screenshot here, but we'll send this out. The blue is the BNC unit, and the pink is the E5052. And so you see they both have absolute phase measurement, but the pulsed phase noise measurement, for example, is an option for the BNC and does not exist on the E5052. The residual or additive CW or pulsed is an option on the BNC, but doesn't exist on the E5052. And then you go right down the list, all the various features down at the end, the frequency counter, the power detector, the tune voltage. Those are all features that we've integrated a way to compare to the E5052. Sorry, it's such a small window, but we'll put a better package together in the webinar follow-up email, along with those fantastic T-shirts.
Yes.
Okay.
I think that about wraps it up, and we stayed within an hour. I know many of you, are currently possibly working, even though it's a Friday, maybe working from home as well. And again, thank you very much for taking the time to be with us today. And again, any questions, concerns, suggestions, please let us know. We're always trying to continuously improve not only our products, but the overall capabilities of our company as well.
Yep. Anything else from you, Mr. Louder?
I think we're good.
Yeah.
Okay. If technical support, you can always contact us. We're here 24/7, pretty much 24/7, because we work from home too.
That's right. Great. All right. Thank you very much, everybody. Thank you for the comments and the contributions. Have a great weekend.
Bye-bye.
Bye.
Bye.